Everybody. Welcome to our next topic in this idea of fields. And so what we want to look at today is another extension of our idea of magnetic fields. And what we want to look at today is the magnetic effects on and from wires, and specifically wires with currents flowing in them. So we're going to build on some ideas we hopefully you guys got from grade 11, and also some ideas that we've been talking about in the last couple days in our own topics. Um, and we'll start with something that again is review from grade 11. And again, of course, we'll build on it to discuss some more topics that we're doing today in grade 12. So hopefully you guys remember Oersted. And Oersted was one of these scientists who worked with electricity and magnetism in their infancy. And he discovered that a wire carrying a current, so what we've got like over here, so we have a wire carrying a current, of course, from positive to negative. Um, that is actually going to have a magnetic field around it. And the magnetic field is circular. And so we can kind of get this circular pattern here going around it. And again, we get the direction of the magnetic field using the right-hand rule. Another way to say that this field is circular is that the field at any point, so let's say right here, the magnetic field is actually perpendicular to the wire because the wire is traveling this way and the field is traveling this way. And so that would make it perpendicular. And anywhere else along the same spot, so let's say right here, the field is this way, and the wire is this way, and notice again those two vectors are perpendicular. So everywhere along that field, the wire is perpendicular to the magnetic field. All right, so Oersted discovered this, published some results, and then this guy named Ampere, again you probably heard the name Amp before, and Ampere came up and said that's pretty cool. Let's try and do some more interesting work with that, and he came up with Ampere's law. We're not going to go over too much of the derivation behind it, where that came from, but Ampere's law, is given by this expression here in the blue background. Along any closed path through a magnetic field, the sum of the products of the scalar component of the magnetic field parallel to the path segment with the length of the segment is directly proportional to the net electric current passing through the area enclosed by the path. And that's a very, very wordy statement. So let me try and break that down for you. So what that means is, if we take a look, if we imagine that we have um, a wire here, so this wire here in red, and I imagine taking any path. In this picture, it's a circle, but let me draw some arbitrary path. Let's make it a square. If I imagine this square, and I imagine going across every little tiny section here, and I add up the products of the magnetic field that's parallel to this segment, and the length of this path segment, it's going to be proportional to how much current is passing through this whole square here. And the current passing through is this I. So if let's say 2 amps is flowing through here, and I add up all the magnetic field parallel to this box along the entire path, it would be, let's say, I don't know, 12. But then if I make this number, I increase the current to 4 amps, this would then be 24. So this would be actually parallel. So we can say then there's some sort of proportional relationship between the two of these things. But let's just confine ourselves to a circle here for right now. And if we do that, we end up with what's going on over here. So let's imagine that we're going to go around this circle here, at some radius r. And the nice thing, again, we decided before is that Oersted discovered the field is perpendicular everywhere to the wire, or really it's along this circle everywhere. So we're going to say that the sum of the magnetic fields along any sort of path length is just given by the parallel component. So we can drop this subscript here. And so really all I have to do is add up the length. And since the circle, it's just 2 pi r. And so what we can get from this is that the current, so where am I here? So the current, oops, sorry about that. Let's try that again. What I can say here is that the current is proportional to B times 2 pi r. And of course, to make anything proportional into an equality, you have to add a constant. And this constant is given mu naught. Mu, again, is that Greek letter, kind of like an M, kind of like a U. And it's called the permeability of free space. This is one of those fundamental constants of the universe. It relates how strong magnetic fields are to electric fields and currents. And certainly if you continue on in physics, you'll see this kind of popping up at a lot more places, but we can leave it for right now and say it's just a constant. And it's given by the value of 4 pi by 10 to the minus 7. So here is kind of Ampere's law. That's true. Notice the assumption we made here. We're saying that the magnetic field at any radial distance from this wire is given by this expression. So if I want to find the magnetic field at, let's say, a distance r from this wire, that's how I do it. So any distance away from any straight wire, so if I want to know, let's say, what is the magnetic field at this point, all I need to know is I, the current flowing through that wire, and R, the distance flowing, or the distance away from where that wire is. And I can get an expression for B, the magnitude of the magnetic field. And how would we get the direction of the magnetic field? Well, we still go back to Oersted and his right-hand rule, this idea of perpendicular to the current at every point. And we can go through and use that right-hand rule to figure that out. All right, awesome. So what does this mean? Well, it means, again, just like in grade 11, a wire produces a magnetic field. It still circulates like we taught you in grade 11, but now we can actually quantify it. How much magnetic field does a wire produce? What sort of field will come off of every wire depending on its current? So I think you can agree it makes sense that the further away you are, the lower the magnetic field, and the bigger the current, the higher the magnetic field. So let's do an example. And see if we can kind of get a feeling of this. So let's imagine that we're about a third of a meter, or a ruler, give or take, away from a wire carrying a current of 4.5 amps. And again, I'll do this for you in class one day. I'll put a current of about this much through through a wire, and we'll look at the effects we can get from this. But we're going to put a current of 4.5 amps through this wire. We're going to be about a third of a meter away, and we want to know what is the magnitude of the magnetic field. And then later, let's compare it to Earth's magnetic field, which has a value on Earth of around 50 microtesla. So of course it does change depending where you are, but let's just say for where we live in Milton, it's 50 microtesla, pardon me. So how are we going to do this? Well, let's use Ampere's law. So Ampere again said that the magnitude of the magnetic field is just given by mu naught I over 2 pi r. And again, we know the current, we know the we know the permeability of free space, we know the distance away from the wire, so we're just going to plug our numbers in. I'll leave that to you to verify, but I'm getting 2.57 times 10 to the minus 6 Tesla, or we can write that as 2.57 microtesla. So what does that mean? Well, that means our magnetic field from this wire is quite a bit weaker than the Earth's magnetic field. And 4.5 amps is actually quite a large current. To put that in perspective, the circuits in your house, depending, of course, you can have higher or lower, but most circuits in your house have current or circuit breakers that shut off with currents anywhere above 10 or 20 amps. So you're not really going to be getting huge amounts of currents flowing in your walls. So 4.5 amps is quite a large amount of current, and we still don't get a very large magnetic field compared to the Earth. So this is why we really don't notice the effects. We don't see like all of a sudden things sticking to your wall because there's a current flowing. You turn your light on, and and I don't know, the coins out of your pocket stick to the wall, because you need a whole lot of current or be very, very close for this effect to become really, really important. But again, if you continue on in physics, you'll see this effect pop up a lot more. All right, so there's the magnetic field from a wire. Let's actually build on that a little more and say, well, we know that a current carrying wire produces a magnetic field, but what's going to happen if we put a current carrying wire in a magnetic field? Well, just like anything else we'd expect, if it has a magnetic field, it will interact with things with a magnetic field of their own, so it will experience a force. And this also does make sense because this is just an extension of the magnetic force we talked about last time, because a current is really just a whole bunch of charges that are flowing. So if we have a current flowing in a wire, it's just the exact same sort of scenario, except we have a whole bunch of charges that are being pushed. And since they're the same sign of charge flowing in the same direction, they're going to be pushed in the same direction, which means the forces are all going to add up. So we're going to get a large force. And so you're going to see here is kind of the expression for the force acting on a wire. It's going to be pretty similar to our force from the other day of QVB sine theta. I'm not going to go through the derivation here, but it has to do with what current means. So if you remember from grade 11, that current is defined as charge flowing per time. And so we can actually get an expression then that relates all this together. And again, if you're interested, I can certainly go over in class with you. But this is our sort of expression for a force acting on a wire carrying a current. So you'd expect a force magnetic field to be in there. You'd expect the sign to be in there just because, again, it wasn't there for the force on an individual charge. So why not for a whole collection of charges? And you'd also expect it to be on the length because the longer the wire, the more charges that are flowing as well. The same rationale could apply for the current. And we do the exact same thing for the direction of force is going to be the right-hand rule. Yet again, luckily it's the same idea. We have fingers being the magnetic field, your thumb being the current, and the force is just coming off of your hand. You can imagine your hand is being used to push the wire in this case. And this force is also called the motor principle or the motor force. And you might imagine why that this is actually the principle that is used to make electric motors function. So any electric motor, from a car to a hobby car to an electric fan to anything that works from an electric motor, this is the basic physical principle that makes it work. Um, and so you have a wire that's in a magnetic field, so it has a force on it, which then can cause motion. So we're transforming electrical energy into kinetic energy. And so this is called the motor principle. All right, so we've talked about the magnetic field caused from a wire. We've talked about the magnetic field effect on a wire. Now, the last one we have to really talk about, and I'm going to just give you a brief intro right now, is the magnetic effect between two wires. Because one wire produces a magnetic field. So if I have a wire here that has a current flowing through it, let's make the current, I don't know, red, flowing like this. I'll call this I1. We can agree then this will create a magnetic field. And if I have another wire over here, oops, pardon me there, another wire somewhere over here, I'll call it wire number 2, having another current flow. It's also producing a magnetic field. So we have two objects that are producing magnetic field, and they're close together. So what are they going to do? Well, they're going to interact with each other. They'll actually have a force exerted on each other. Um, and we're actually going to work on this in class tomorrow. So I'm not going to go through this with you right now. I'm actually going to have you guys work out an expression for what this force will look like. But if you want to think about this in the back of your mind, how we could actually come up with that, that'd be a great thing to get you working on. And that's where I'm going to leave you for today. So hopefully this kind of makes sense, just building on some topics we've talked about so far. And think about this a little bit tonight, and we'll look at this in class tomorrow. Have a great night, everybody, and I'll see you tomorrow.